Newton's method for minimization. From the previous method, okay, you see that the steeper descent, we use the steeper descent with exact line search to minimize a quadratic function. Then it contains many steps before, okay, to achieve the minimum, right? So if we apply the steeper descent to other nonlinear function, then you can see its performance. With a difficult function, or when the eigenvalues when the eigenvalues of the largest eigenvalue of the H geometric at the minimum point and the smallest eigenvalue of the H geometric at the minimum point are very different, then the convergence rate is very slow, can be very slow. Even we implement the method in the best possible way, right? We use the method with exact line search. Then you will see that there are methods that are far better than that. And so the steeper descent is at one extreme, which can be very slow and not efficient. Now we'll see another method, which is in the other extreme, which is a Newton's method. Now you'll see that so the idea is this: the steeper descent is one end. Is at one end, the steepest descent, whereas Newton's is at the other end. The steeper descent R is equal to 1. This is a linear convergence, okay? And Newton method R is equal to 2. We will prove that later. But then you will see that when we apply the Newton's method to quadratic function with exact line search, it converges only within one iteration for any Q matrix. Okay, we'll look at that later. But first we see how can we derive this method. Now when we solve, in solving optimization problem, Newton-Raphson is used, right, to find. We apply Newton method. We apply Newton-Raphson method to solve the first order necessary condition. From chapter 4, we know that we apply Newton-Raphson to find a stationary point, because we know that if x is not if the point x star is not a stationary point, then the point x star cannot be it can be neither a local minimum nor a local maximum of the function f, right? So and that's the idea, and that's the idea of the application of Newton-Raphson to find a stationary point in a very primitive way. And we'll see what happens first in this primitive way, and then we will modify that to guarantee that in this procedure, then we can guarantee that the cost function is reduced in every iteration. How can we do that? Okay, we'll see. First, we apply. You see that when for a nonlinear function f, right, and this is the first order necessary condition, right? The gradient of fx equal to 0, right? And this form, and this forms a set of nonlinear algebraic equation. So we will apply Newton-Raphson method to solve this, to find a solution to the set of nonlinear equation grad of fx equals 0, right? And in this one, we can show that the Jacobian matrix of the gradient of the function f is in fact the Hessian matrix of the objective function f. Okay, the Jacobian of the gradient is in fact the Hessian matrix of the objective function f in this case. Now with that, then we Okay, so this is we substitute all that into the standard Newton-Raphson formula. Then what we have is Newton's iteration for minimization. When we solve the nonlinear equation, okay, the f of x is equal to 0. Okay, this is the f is a vector, right? F maps Rn to Rn. Okay, so the Newton-Raphson iteration is Newton-Raphson iterations is xk plus 1 equal fxk, right? Minus the inverse of the Jacobian, right? Multiply with f xk. Is that correct? Is that correct? Whereas if the minimization of the objective function f, which is Rn to small f, Rn to R, then the necessary condition is the graph f of x equal to 0, right? So the Newton iteration for this is xk plus 1 equal xk minus the geometric inverse multiplied with the gradient of fxk. Okay, they are similar but not the same, right? Now we go back to the slide. Okay, then this is how we obtain the Newton-Raphson. This is how we obtain the Newton formula for minimizing the function f, right? And the formula, the iteration 5.11 is known as Newton formula for minimization, or the classical Newton's method for minimization. Now you see that now, okay, this is this one. So now you can see we compute the search vector SK, by solving the a system of linear equation. The Hitcher matrix multiplied with SK equals minus fxk, right? We compute the search vector SK from solving a system of linear algebraic equation. This, right? We solve this linear equation. Okay, so we solve this linear equation to obtain the vector SK. Once we have the vector SK, then we update the iterate xk plus 1 by xk plus 1 equals xk plus sk. Just very similar to the when we do Newton-Raphson, right? Okay, now you can see first, when we solve the Newton-Raphson, sometimes Newton-Raphson converges, sometimes it does not converge. Right? So when we apply Newton-Raphson to the first order necessary condition, we have the same situation. It will be to too optimistic to assume that the Newton-Raphson for minimization will converge, will always converge. This is not possible. Okay, now, so what can we do here? So what we do is, although it does not always converge, right? But we will introduce some procedure to force the iteration 5.11 so that the cost function is reduced, is guaranteed to reduce in every iteration. Now imagine if you start from any starting point, and then when we solve this, right, when you do iteration 5.11 in such a way that the cost function is guaranteed to reduce. Okay, so we hope that eventually will converge to a local minimum sometimes, somewhere, right? So what we do is that okay, now we just skip this first. What we do is that, okay, what we do come to this, right? So what we do is we introduce an additional variable, lambda, which is step length. Now, from here, you see that we update the iterate. This is xk, then this is sk, right? And this is the x plus 1. We do not, okay? Now you can see, once we have the search vector sk, then we can do the one-dimensional optimization, right? So we add this into the unmodified Newton's formula 5.11, so that when we, okay, so for each search vector sk, we find the minimum of fxk plus lambda sk. So that now the function is reduced to the minimum in each direction. Okay, this is how we implement a Newton method with exact line search. Okay. Now, okay. And so this formula is the modified Newton's, is known as the modified Newton's method, or is the Newton method that we use in practice. We never used a 5.11 in minimizing the function, right? We used this is the Newton method that people use in minimization, the 5.13. And this is known as the unmodified Newton's method. Oh, sorry, the modified Newton's method sometimes. But even if we say Newton's method, it means the 5.11, not the unmodified formula. This is the Newton method that we use. Okay, people use. So now you can see that from from the unmodified or the classical Newton method, right? We introduce the parameter lambda k. Okay. Now, okay, now we look at some analysis first. Now we look at the proposition 5.244. Now this is okay. So it's when we use Newton method to minimize a quadratic function fx equal to 1/2 x transpose qx plus p transpose x, right? Where q is positive definite. Then it takes only one step for any starting point. That means for any x naught. Now you can see this is very different from the This is very different. This is very different from the steeper descent. Okay. How can we prove this? Okay, we will prove this. Although I think in the slide I said this is left an exercise for students, but no student will ever do this. So when it converges within one step, what does it mean? It means that for any x0, x1, if it takes only one step, that means x1 is the solution. Right? And what is the value of the solution? When fx, right, fx equal 1 over 2 x transpose qx plus p transpose x. Okay, q is PDF, positive definite. Right? So the x star is equal to, we know this before from previous lectures, we know that x star is minus q inverse p. Right? So if you want to prove this, now you see that we have to prove. So we have to prove that x1 is equal to 1 is x1, you're right, x1 is equal minus q inverse times p. This is what we have to prove for Newton's method. Now, this is what we have to prove for any x0. Now, what is the formula for that, for the Newtons? The Newtons is the Newton formula, the Newton's method. What is the formula for this? Is the x1. We know that, okay, x1 is equal x0 plus lambda, right? Plus lambda naught. Multiply with, I'm sorry, we don't have that. Even we implement this with, okay, we implement this with the unmodified Newton method, okay? Where we implement the Newton's method without line search. It reaches the minimum within one step. Okay, this is what we have to prove. This is a without line search. Without line search. Okay, without line search. So what is S? The direction S naught is Q, right? The Hitcher matrix Q S naught is equal to the grad Q X naught plus E, right? Am I right? The Hitcher matrix multiplied with S is equal to the minus gradient. The gradient of this is the gradient. What? No. What happens then? Okay. So the gradient of f grad fx is qx plus p. So the gradient at the point x naught is equal to qx naught plus p, right? So what is s? What is s? The s is the minus q inverse multiplied with qx naught plus p, right? Then we expand this. This is we multiply the qx naught. Then what we know is that this is equal to the minus x naught minus q inverse p. Q inverse times p, right? This is x naught. So the x1. So the x1 is x naught plus x naught, which is the x1 x naught minus x naught minus q inverse p, and therefore is equal to the minus q inverse p as we want. So now you can see if we implement the unmodified Newton's iteration, right? It reaches the minimum within one step. Okay. And next we will prove this. Okay, this is the result when we apply Newton's method. Okay, without line search. We apply Newton's method without line search. Okay, and this theorem, with this, I think this theorem is pretty standard. But I have to say this: when we look at, okay, if you read the text shown as Zach's, okay, I think the author assumed. I think the author do not use Lipschitz condition, and therefore they have to say something about the third derivative, which cannot be expressed, and we don't need that. Okay, so the proof in the Chong and Zach, I'm not sure that in the fourth edition the author will have some improvement or not. Okay, but in the second or the third, the proof is still this is not standard, but this is the pretty standard one. You find in any numerical optimization books, and here they assume that the Hessian matrix satisfy a Lipschitz condition. Now, what is the use of this in mathematical analysis? When we use Lipschitz condition, okay, Lipschitz condition is used when we want to avoid using the derivative. So if you want to avoid, okay, if you want to avoid using the derivative of the object you are talking about, then we use Lipschitz condition. We can prove that without, okay, without derivative, using Lipschitz condition. This is how we use Lipschitz condition. Here, this is the Lipschitz condition on the Hessian matrix. So if you don't want to mention to the derivative of the Hessian matrix, right? So in this case, the derivative of the Hessian matrix, what is that? We don't know. This is the derivative of the Hessian matrix with respect to the vector x. When you differentiate a matrix with respect to a vector x, then I think the third derivative cannot be expressed by using matrix. You have to use tensor, right? Which is much more complicated. But when we use Lipschitz condition, if we can do that, then and in this case we can do that. Okay, we can do that, and this is what. So here we assume that the function f is twice continuously differentiable, and we also assume that the Hessian matrix satisfy a Lipschitz condition, which is stated as the norm of the Hessian matrix between the point x and y. Okay, the norm of the Hessian matrix of fx, the norm of Hessian matrix at the point x minus the Hessian matrix at the point y, okay, is bounded by a number constant L multiplied with the norm of x minus y. Where L is a positive constant. It's called Lipschitz constant. Okay, Derek. Okay. If the Hessian matrix satisfies the Lipschitz condition in a neighborhood of a local minimizer X star. So that means it means that the function f, the H matrix of the function f is continuous, right? In the neighborhood of the local minimizer X star. Okay, and if the iterate xk is sufficiently close to x for some k, that means after when we do the iteration for some time, then the xk gets to somewhere near to the minimum point, not at the minimum point, but somewhere near that. Okay, then it will converge with a quadratic rate of convergence. Okay, so when we use the Newton's from this, okay, I think at the moment we skip the proof because it takes a long time to prove this, but I think okay, now the point is this: when we use the Newton's method without line search, okay, then it converges with quadratic rate of convergence according to this theorem, right? Now you see now we have two methods. When we use the Newton's method, it's the rate of convergence is quadratic. When we use, which is very fast, when we use the steeper descent, the rate of convergence is linear. Okay, it's linear. After Newton's method, we will consider quasi-Newton and conjugate gradient methods, which are somewhere between this. Okay, we find that Newton's method is fast. It can be fast, but it doesn't. Okay, it's fast, but it doesn't guarantee convergence. First, and second, I think the major drawback of using Newton's method is that it requires second derivative. Now, in many problems, as I said before, we okay, when the function f, when the objective function f is not known analytically, that means if you don't have the formula for the function f, so compute gradient is not easy. But then if you have to compute the second derivative matrix, that's even more difficult. Okay. For example, if you in power system, if you want to minimize something, okay, the operation cost or some loss or whatever, then you have to solve the network equation in order to compute the objective function f. So in that way, for even with the 10, okay, with a power system with 10 or 20 buses, it's impossible to compute the function f analytically. It means we don't have analytical formula for the function f in general. So what we have is that with the sum vector x, the decision variable x, then we can compute fx. This is what we have. Or if you design electronic circuit, okay, if you want to optimize some parameter in the circuit amplifiers, okay, if you want to find some resistor or the capacitors, that minimizes the, let's say, if you want to maximize the bandwidth of an amplifier, right? Then and if your circuit has many elements, then it's not easy to find the gradient of the function f. Now you have to approximate the gradient some way by approximation technique. But then if you see that we already have some burden, but if you with that burden, if you have to compute the H matrix, it's even worse. And this is why Newton method, people try to implement Newton's method in the way that we don't need second derivative matrix. Okay, that's the whole picture, to see the whole picture. Now, okay, now we look at the details of the Newton's method, okay? And so when, okay, now, okay, when we implement the Newton's method for a general nonlinear function, we implement Newton's method, okay, with the formula 5.113, which is Newton method with line search, okay. Then with the line search, it come to the question: when we do the line search, how can we guarantee that the lambda, okay, the step length we choose is positive? In the case of the steeper descent, is guaranteed by the property, right? Because we already we proved that already, right? Last time that in every search direction of the steeper descent, it has descent property. For Newton's method, it doesn't always have descent property. Okay, then now when it will have descent property, now we consider this. Okay, we look at the proposition, this proposition. What happens? Okay, it doesn't. Okay, we have to go. In this proposition, we consider a method in which the search direction, the search vector Sk, is expressed at minus a matrix Hk multiplied with the gradient at the point Xk. Okay, then you can see that if the search direction, now you see for a Newton's method, the matrix Hk is the H matrix, right? Is the H matrix inverse, right? You see this. For Newton's method, the matrix Hk is equal to the inverse of the matrix Hk is equal to the inverse of the H matrix of the function f at the point xk, right? And so we consider this as a general form, so that we can consider we can apply this to other methods as well. Okay, so we find that when the matrix Hk is positive definite, then the search vector Sk, which is equal to the minus Hk multiplied with the graph fxk, always has a descent property. Now that means if the H matrix is positive definite, or if you get, now you imagine when you minimize a function, the H matrix at as a local minimum is positive definite, right? The H matrix of the function f at a local minimum is positive definite. Otherwise, it cannot be, right? Am I right? Okay. So, and with the continuity property in the neighborhood of a local minimum, the H matrix of the function f in the neighborhood is also positive definite, right? So that means from this we can deduce that when the Newton's iteration is getting near to the solution, then the step length is okay. The Sk has the same property, and therefore the step length is also positive, right? It cannot take negative values unless you are far from that. if you find that the step length, so okay, so if when the H matrix HK is not positive definite at the iterate XK, then sometimes SK has the same property. So we can check if SK transpose graph FXK is negative, then right? If SK transpose graph FXK is negative, then we know. So we check, you compute the directional derivative. When the directional derivative, right, which is the SK transpose graph FXK is negative, then you know that the alpha, the lambda is positive, right? Is positive. If the SK transpose graph FXK is not negative, let's say it's positive, then you know that you have to go backward. You have to go backward. To go backward, then how can we apply this? So we change the search direction from we multiply -1 to the search vector, and therefore you search backward, right? And then we can still apply the procedure, the line search subroutine or the line search function that you write before for the positive step length. Now I'm talking about when we write the code. I'll write it down. I cannot use the screen. So when this is the gradient at this point is the direction of the derivative, right? This one, the gradient, the slope. The slope is SK transpose graph FXK. When we know that we compute this further, if we know if this is negative, then we know that the lambda that minimizes this one takes the positive value. Then you do then you search along it, right, in the positive axis of lambda. Right? Then if this, but in now, suppose we have a function like this. The test, the red one. Then you compute the gradient at this point. Now the SK transpose that FXK happens to be positive. Right? The positive. Then in positive, then for this positive, then we know that it has to go into this direction so that you find the minimum at this point. Right? So how can we do that? If we I think in programming technique, we change SK to -SK in the end, right? Am I right? We change SK to -SK to find this lambda. Then if you write a procedure, if you have a procedure already for going into the positive axis, then you can apply that, but you just change the sign of the SK. And then you can use the same procedure. Otherwise, you have to write the program to cover both cases. To write the program to cover both cases, the code will be more complicated than to handle only the positive value. The case of the positive value of lambda, right? So when implement the Newton's method, now you can say that lambda is positive or negative. Okay, the lambda that minimizes fxk plus lambda sk is positive or negative, depending on the directional derivative. Now you can see the role of the directional derivative in minimizing the nonlinear function f. Right? So before the statement is said, you don't have to check because it's guaranteed by the theory. But for the Newton's method, it's not guaranteed. Okay, and when we implement this now for this issue, then when we for the other two class of methods, we try to impose some condition in which we can guarantee the descent property. Yeah, but for Newton's method, we cannot guarantee that. So when we cannot guarantee that, we have to check the directional derivative in every iteration. Okay,